Friends, have you ever looked up at the night sky and felt a sense of wonder about the vastness of the universe? Well, there's a cosmic mystery out there that has astronomers scratching their heads: dark matter. Dark matter doesn't emit, absorb, or reflect light. It's invisible to our telescopes, yet it makes up 85% of the matter in the universe. All the stars, planets, and galaxies we see only account for 15%. Scientists believe dark matter is out there because of its gravitational influence on galaxies. It's like an invisible hand shaping the cosmos. Get ready for a wild ride into the unknown. Alright folks, let's dive into the mystery of dark matter. This elusive substance makes up about 27% of the universe, yet we know so little about it. Imagine you're at a carnival, standing in the middle of a spinning carousel. The lights, the sounds, the excitement, it's all around you. The horses go up and down, round and round, but you stay put, right? That's because of gravity. It's the force that keeps you grounded. Without it, you'd be flung off into the air. Now, imagine that carousel spinning so fast that the horses should fly off into the crowd, but they don't. They remain in place, defying what you'd expect. They stay perfectly in their circular paths. It's almost as if an invisible hand is holding them in place. That's kind of what's happening with galaxies. They spin at such high speeds that, without some extra force, they should tear apart. Astronomers have observed that stars and galaxies are moving way too fast for the amount of visible matter we can see. It's a puzzling observation that has led to many theories. It's like something invisible is holding them together, providing the extra gravity to keep them from flinging off into the cosmic abyss. This unseen force is what we call dark matter, and that, my friends, is where dark matter comes in. It's the mysterious substance that acts as the glue holding galaxies together. Think of it as the invisible scaffolding of the universe, the cosmic glue that holds everything together. Without it, the universe as we know it wouldn't exist. We can't see it, touch it, or directly detect it with our instruments, at least not yet. But its presence is undeniable. But we know it's there, lurking in the shadows because of its gravitational effects on the things we can see. It's like a ghost, influencing the world around it without being seen. It's like a cosmic game of hide-and-seek, and we're the detectives trying to uncover its true nature. Every clue brings us a step closer to understanding this cosmic mystery. Some scientists believe it's made up of exotic particles we haven't discovered yet. Particles that interact very weakly with ordinary matter. These particles could hold the key to unlocking the secrets of dark matter. It's a reminder that there's still so much we don't know, so much left to explore. The universe is vast and full of mysteries, and dark matter is one of its greatest enigmas. So, we know dark matter is out there, playing a cosmic game of hide-and-seek. It's like a shadow that we can't see directly, but we know it's there because of the way it influences the universe around it. But what is this elusive stuff actually made of? This question has puzzled scientists for decades, leading to numerous theories and experiments. Scientists have come up with some intriguing candidates for dark matter particles. These candidates range from the very massive to the incredibly light, each with unique properties. One of the leading contenders is something called a WIMP, which stands for Weakly Interacting Massive Particle. These particles are thought to be abundant in the universe, yet incredibly difficult to detect. WIMPs are hypothetical particles that are thought to be much heavier than protons and neutrons. Their massiveness makes them a strong candidate for dark matter. But here's the catch. WIMPs interact very weakly with regular matter, which is why they're so hard to detect. This weak interaction is what makes them so elusive. Think of it like this. Imagine a crowded room full of people. It's bustling and chaotic, with everyone moving around. You're trying to walk through, but everyone's bumping into you, making it difficult to move. You feel every nudge and push. Now imagine a ghost trying to walk through that same room. The ghost would pass through effortlessly, without any physical interaction. They could glide right through the crowd without anyone even noticing. This is similar to how WIMPs interact with ordinary matter. That's kind of how WIMPs are thought to interact with ordinary matter. They're like cosmic ghosts. They are present, but their interactions are so weak that they go unnoticed. Another candidate is the axion. Axions are fascinating because they were initially proposed to solve a different problem in particle physics. Axions are hypothetical particles that are much lighter than WIMPs, but they're also thought to interact very weakly with ordinary matter. This weak interaction makes them another strong candidate for dark matter. They were first proposed to solve a problem in particle physics, but they quickly became a popular candidate for dark matter. Their unique properties make them a subject of intense study. And then we have sterile neutrinos. These are a special type of neutrino that don't interact via the weak force like regular neutrinos do. Neutrinos are tiny, almost massless particles that zip through the cosmos at nearly the speed of light. Sterile neutrinos, if they exist, could be a form of dark matter. Some physicists believe that dark matter might not be a particle at all. This opens up a whole new realm of possibilities. They propose that it could be a new kind of force, something we haven't even begun to understand. This idea challenges our current understanding of physics and could revolutionize the field. Chapter 3. How can we detect dark matter? So we've got these invisible particles, or maybe even forces or dimensions, shaping the universe from the shadows. They don't emit, absorb, or reflect light, making them completely invisible to our eyes and even to our most advanced telescopes. The question is, how do you catch something you can't even see? It's like trying to catch a ghost with a butterfly net. Scientists have devised some ingenious methods to try and snag this cosmic phantom. These methods range from deep underground experiments to high-altitude space missions. One approach is to build detectors deep underground, shielded from all the cosmic rays and other particles that rain down on Earth. These underground sanctuaries provide a quiet environment, free from the noise of other particles. These deep underground laboratories are like fortresses of science, designed to detect the faintest whispers of dark matter particles interacting with ordinary matter. They are equipped with highly sensitive instruments that can pick up the slightest signals. One such experiment is the Xenon experiment, located deep beneath the Gran Sasso mountain in Italy. This facility is one of the most advanced in the world for dark matter research. This experiment uses a giant vat of liquid xenon, cooled to extremely low temperatures. The xenon atoms act as targets for dark matter particles. The idea is that if a dark matter particle collides with a xenon atom, it will produce a tiny flash of light and an electrical signal that scientists can detect. This signal is then analyzed to determine if it could be a dark matter interaction. Another way to hunt for dark matter is to send experiments into space. Space offers a unique vantage point, free from the interference of Earth's atmosphere. Up there, above Earth's atmosphere, detectors have a better chance of catching a glimpse of these elusive particles. The lack of atmospheric interference allows for clearer and more precise measurements. The Alpha Magnetic Spectrometer, or AMS-02, is a particle detector mounted on the International Space Station. It has been a crucial tool in the search for dark matter. It's been collecting data on cosmic rays for over a decade, and scientists are hoping to find evidence of dark matter particles among the trillions of particles it's observed. The data collected is meticulously analyzed for any anomalies that could indicate the presence of dark matter. Then there are particle colliders, like the Large Hadron Collider, or LHC, at CERN in Switzerland. These massive machines accelerate particles to near the speed of light and smash them together. The hope is that by recreating the conditions of the early universe, we might be able to create and detect dark matter particles directly. These experiments are pushing the boundaries of our understanding and bringing us closer to uncovering the mysteries of dark matter. Chapter 4. Could dark matter be a new kind of physics? We've talked about the what and the how of dark matter, but now let's dive into the truly mind-bending possibility. Could dark matter be evidence of physics beyond our current understanding? The standard model of particle physics, our best current explanation of the fundamental building blocks of the universe, has done a pretty good job so far, but it completely whiffs on explaining dark matter. This glaring omission has many physicists wondering if we're missing a crucial piece of the puzzle, a piece that could revolutionize our understanding of the cosmos. Some physicists propose that dark matter interacts with a new kind of force, a force that doesn't affect ordinary matter the way gravity, electromagnetism, or the strong and weak nuclear forces do. This new force would exist in a separate dark sector, interacting with dark matter particles in ways we can only begin to imagine. It's like having an entire shadow universe operating alongside our own, interacting with us only through the faintest of whispers. Then there's the idea of extra dimensions. String theory suggests that there could be more than the three spatial dimensions we experience in our everyday lives. These extra dimensions would be curled up and hidden from our perception, but dark matter particles could be vibrating in these hidden dimensions. These are just a few of the mind-boggling possibilities that dark matter presents. Chapter 5. Will we ever detect dark matter? So, after all this talk of cosmic mysteries and mind-bending physics, the big question remains: will we ever actually detect dark matter? Well, I'm an optimist at heart, and I believe that with enough ingenuity and perseverance, we can unravel even the most confounding cosmic mysteries. The search for dark matter is like a thrilling detective story full of twists and turns, dead ends and breakthroughs. The good news is that physicists around the world are hot on the trail, developing ever more sensitive detectors and devising new strategies to catch this elusive quarry. Some scientists believe that we might be just a decade away from a major breakthrough, a discovery that could revolutionize our understanding of the universe. Of course, the search for dark matter hasn't been without its challenges. Experiments have come and gone, some yielding tantalizing hints, others leaving us with more questions than answers. But that's the nature of scientific exploration. It's a process of trial and error, of constantly refining our methods and pushing the boundaries of knowledge. One thing's for sure, finding dark matter won't be easy. It might require developing entirely new technologies, or perhaps even a paradigm shift in our understanding of the fundamental laws of physics. But the potential payoff is enormous. The search for dark matter is a testament to the power of human curiosity, our insatiable desire to understand the universe and our place within it. It's a journey into the unknown, a cosmic detective story that has captivated scientists for decades. While the mystery of dark matter remains unsolved for now, the journey itself has been filled with incredible discoveries and mind-blowing possibilities. So, stay tuned, my friends. The hunt for dark matter is far from over, and the next big breakthrough might be just around the corner.